Hi, this is an AP video, AP Chemistry. We're going to cover topic 3.4, the ideal gas law. And I think, most of you probably remember the equation for the ideal gas law. It is pressure times volume equals the number of moles of the gas times the ideal gas law constant and then times temperature. So when I look at this equation, well, first of all, I need to tell you that because of the value of the units that we're going to use on our R, we're going to use the unit of R for what we're going to do is liters, atmosphere, inverse, Kelvin, mole. So because of that, we're going to want to have our pressures in ATM. So if we need to convert those, we should do that. Our volume should be in liters. And then our temperature, and when we do gas law calculations, are always in Kelvin. And what we remember, and we have this on our sheet, our equation sheet, is Kelvin is Celsius plus essentially 273. I think it's 273.17 exactly, but let me see. I have that on your sheet somewhere. But so if I look at the equation, PV nRT, I know these two variables, assuming I'm holding the moles and the temperature constant, those are inversely proportional. So as pressure goes up, volume goes down. And then the relationship between pressure and moles, this is going to be a direct relationship. As I increase the number of moles, there's going to be more particles that that will exert a force on the interior surface of a container through collisions. There's just going to be more collisions. Similarly, pressure and temperature, assuming you're holding the amount of the gas constant and the volume of the container constant, there's a direct proportion there. Particles are moving faster. There's going to be more force exerted on the interior walls of the surface through collisions. So the pressure will go up as temperature goes up. If I rearrange, you can also see it this way where, my direct proportion is with the variables that are in the numerator, and my indirect proportion is with my variable in the denominator. So just looking at our formula sheet, we do have the ideal gas law here. The combined gas law essentially is directly related to the ideal gas law. We're also going to be looking at Dalton's law of partial pressure, and we're going to derive a different form of the ideal gas law using these variables. So, and we'll be looking at mole fraction. So before we do that, let's talk about the actual value of the ideal gas law constant. It's on our sheet. We don't need to memorize it. But I will tell you that if you assume that you have 1 mole of a gas at STP, which is standard temperature and pressure, which is 0 Celsius, which is 273 Kelvin. If you have 1 mole of a gas, it's going to occupy 22.4 liters. So if I rearrange this equation and solve for R and plug those numbers in, I will get the number value of R. So if I put in 1 ATM times 22.4 liters over 1 mole of a gas times 273 Kelvin, I do get 0.08205128, blah, blah, blah. And you can see the unit of my constant R, liters, atmosphere, Kelvin, and mole, inverse Kelvin, inverse mole. So the ideal gas law incorporates all of the gas laws. So you can kind of look over these slides and see the relationship. If the other variables are constant, there's a direct proportion between number of moles and the volume, which is Avogadro's law. Temperature and pressure are directly related. We talked about that earlier, but that is Gay-Lussac's law. Charles volume and temperature, we did not cover that, but as the temperature increases, if the container can, it will expand. And then Boyle's law, we did cover this in the beginning, the inverse relationship between pressure and volume. Here is some other, just the mathematics of these, and the combined gas law here, which is on your equation sheet. If I put moles in here, and then I can derive the ideal gas law. So example 9 now is asking me, I would read this and then pause the video and go back and think about, there's some changes being made to one or more variables of a gas, and then what will the effect be? Predict the effect on the other variables, but do this without a calculator. So first scenario is you have a gas in a rigid container, so the container volume is not going to change. So our volume is going to be constant. They also didn't mention the temperature changing in this scenario, so we'll assume that's constant. The pressure was originally 6 atm, and then some of the gas was let out when it was opened, and it dropped down to 3 atm. So we can assume that the moles decreased by 1/2. So for example, if I had 10 moles here, then I would have had 5 moles here. So half of the moles got released. Next scenario, you have a balloon that's hot on a hot day, and then you take it outside and it kind of shrivels into a smaller balloon. The volume of the balloon is decreased, so we know that. And then how are the other variables changing? So we know the volume goes down. We know that the temperature decreased by 1/6 because the volume and the temperature are directly proportional. When you take a balloon from outside to inside and vice versa, you can assume that the pressure is constant. There isn't much of a pressure change between inside and outside. And then also you would assume that the balloon isn't leaking, so the moles of the gas in the balloon are constant. Last scenario, we have gas in a movable piston. So we have a piston, and we're going from an initial volume of 12 liters, and then we push down, and now we have a volume of 6 liters. So you can see that our volume decreases by 1/2. In the question, they also say it went from 400 Kelvin to 800 Kelvin. So we know that the temperature, did it decrease or increase? Whoops, I'm on the wrong question. Yeah, the temperature doubled from 400 to 800. And the number of moles, if we're assuming this is a sealed container, is constant. And then, the pressure should be multiplied or increased by 4, a factor of 4. And you can kind of prove that if you do the PV NRT. This is constant. So really your pressure times 1/2 of the volume is going to equal your temperature, which was doubled. So if you solve for pressure, you're going to get 4, and the pressure should be 4 times greater because you're increasing temperature, which increases pressure, and you're decreasing volume, which should increase pressure. Now I'm going to show you that we can rearrange and substitute into the ideal gas law and get other equations. So one thing that we can do with the ideal gas law is if we can calculate the molar mass of a gas if we know its density. So this equation here on your formula sheet is just telling you that moles equals mass in grams over molar mass in grams per mole. So typically, like if we have, 10.2 grams, and then let's say it's oxygen, we would say oops, can't talk, and right at the same time, 32 grams of O2 in 1 mole of O2. So really we are taking the mass divided by the molar mass. So that gives us moles. So now what we're going to do is we're going to substitute into the ideal gas law. Instead of N, we're going to put in mass over molar mass. And I have that right here on my formula sheet. Then if we divide both sides by V, the volume, and isolate the pressure, I have the equation mass times the constant, our ideal gas constant times temperature over volume times molar mass. I can isolate this part out, and this is density. So now I can substitute in density. So pressure equals the density of the gas times the ideal gas law constant times temperature over molar mass. And if I want, I can just rearrange that and solve for molar mass. So this is a pretty easy derivation of how you can take the ideal gas law and use it to solve for moles. So let's do one example here. I would definitely pause the video and try it. In the question, they're telling us that the pressure of the gas is 1.50 atmospheres. The temperature is 27. Add 273.17. That's going to be about 300 Kelvin. Density is 1.95 grams per liter. And we're being asked for the molar mass. So we're going to use the form of the equation that we just derived, taking the density times the ideal gas law constant times temperature over pressure. So I'm going to take my density times, I'm going to put my units in. All over my pressure. I'm going to show you that if you put your units in, it's nice because you really should feel more confident that you did this correctly. So my Kelvin degrees cancel, my atmospheres cancel, my liters cancel, and I'm left with grams per mole, which is the unit for molar mass. So I can feel pretty confident that I did this correctly. When I do, with 3 sig figs, I get 32.0 grams per mole. So that is a scenario that you could see like in a lab if you knew the temperature in the room, the pressure in the room, the density of the gas at that particular temperature, then you could easily calculate the molar mass of the gas and then maybe identify what the gas is. Now we're going to talk about Dalton's law, partial pressures. So gases are a lot of times a mixture of more than one gas. Partial pressure is when we're just talking about the pressure exerted by one part of the mixture, that one particular gas in the mixture. And just so you know, ideal gases behave the same. Most gases behave ideally unless you're in extreme pressures and temperatures, which we're going to talk about in a different topic. An ideal gas, all of the gases behave the same regardless of their identity. So example, carbon dioxide is going to act the same as fluorine, as hydrogen, as helium. So the identity of the gas doesn't really matter. So now we're going to talk about Dalton's law of partial pressure, which is on our formula sheet. Just saying that the total pressure is equal to the sum of the partial pressures of all of the gases that are in the mixture. Now, we're going to also talk about something called mole fraction. So a mole fraction is when you look at the ratios of the moles of just one of the gases in the mixture to the total moles of the gases in the whole mixture. So this is also on your formula sheet. So if I want the mole fraction of, whatever A is, my one gas, I'm going to take the moles of that gas divided by the total moles, and then that gives me the mole fraction. So in this question here, if you want to count with me, there's 10 red particles and there's 5 blue particles. So the mole fraction of the red, remember, it's just going to be the moles of the red over the mole total. And when I do this, I do divide it. I don't leave it as a fraction. And notice there is no unit. So this is the mole fraction of this mixture that is red. So if I were to do the blue, the mole fraction of the blue is going to equal the moles of the blue over the total moles. So in the picture, and there is one hiding up there, so just realize there are 5 molecules, particles, moles, they all work. 5 moles of the blue for every 15 total. So the mole fraction of the blue is going to be 0.33 repeating. Notice the mole fractions of these two add up to 1. Even if I add more than one gas, the mole fractions should all add up to 1. Partial pressure now, since pressure is directly related to moles, which we talked about earlier in the video, we can say also then that the partial pressure is related to the total pressure by using the mole fraction. So we're going to use this equation now. So if I want to calculate the pressure of the red particles, I'm going to take my mole fraction of the red times the total pressure. In this picture, there is a 3 atm. So similarly, if I want the pressure of the blue, I'm going to take the total pressure times the mole fraction of the blue that I had done previously. So the total pressure is 3. The mole fraction of the blue was 0.33. So I get a pressure of 2. And notice, this way I just did that one wrong. I get a pressure of 1. Sorry, I'm reading my paper wrong. But notice that the partial pressure of the blue and the red, because they're the only 2 gases, the total of them should be the same as the total pressure, and they are. So let's try this example. I would pause the video, try it, and then see. So in this question, you have a gas A in a container, and initially it's by itself. It has a pressure of 0.25. That's represented right here on this graph. So that is the partial pressure of the gas A, which is given in the question, and you can read it from the graph, 0.25 atm. Then so you originally have just the A gas, and now you're going to add the B gas and wait and keep pumping it in. And then in 2.5 minutes, you can see it kind of plateaus. So the 1.2 is the total pressure of the pressure of the A gas and the B gas. So this is total. So because of that, I know from earlier that the partial pressure of the gas A and the gas B is going to equal the total. I can easily solve for the partial pressure then of gas B. So all I'm going to do is take the total pressure, subtract the pressure of the A, and when I do that, I get 0.95 atm. So the pressure of the B and the A should add up to the total pressure 1.20, and they do. Now, this way I'm going to add a page so I have more room. So now they want to know the mole fraction of B. So I can use the equation right here and solve for mole fraction. So the pressure of B is going to equal the total pressure times the mole fraction of B. So if I sub in, the partial pressure of B is 0.95 atm. The total pressure is still 1.20 atm, and that will, be multiplied by the mole fraction. So if I solve for the mole fraction, it is equal to 0.95 over 1.20. So I get 0.79 is my mole fraction for the B. Next example, I want you to, again, try pausing and solving this on your own, thinking through the variables, how they're changing, and by what factor. So when I do this problem, the first thing I want to, at least I notice, is that there's 6 moles of argon and 3 moles of xenon. The pressure of the argon is 2 atmospheres, so the pressure of the xenon must be half of that. So now I know PV is nRT, right? And I know that I am going to decrease the volume, which is going to increase the pressure. I am decreasing the volume to 1 liter compared to 2 liters. So my volume is going to go down by 1/2. So my pressure should go up by 2 times. I also know that my moles are increasing. So my pressure will also increase because of that. So what I'm going to do is I am going to write down my new pressure. 2 times this, once it gets into the 1 liter container, would be 4 ATMs for the argon. And because I have half the size of the container, there's going to be a much higher pressure because there's going to be more collisions with the side of the container. The pressure of my xenon is going to be times 2. So my new pressure is going to be 2 atmospheres. So when they both go into the small container, the sum of those 2 pressures is 6 ATM. So that is my answer here. So I have to look at the variable and then how does it change? I know that as the volume went down, the pressure goes up. If the volume goes down by half, the pressure goes up by 2. If the volume goes down by 1/3, the pressure goes up by 1/3. By 3, sorry. Okay, let's keep going. Example 3 here. So here we have the figure below represents 2 identical sealed containers, both at 450. The container on the left has only carbon dioxides, and they have a molar mass of 44 grams per mole. The sample on the right also has CO2, but it does have some molecules of O2. But notice that N equals 8 for both. So, assuming that both samples behave ideally, the pressure in sample 2 is most likely which of the following? So, the pressure in sample 1 is 1 ATM. And if the gas is behaving ideally, then the identity of the particle, the identity of the actual gas being CO2 or O2 or anything, hydrogen, helium, it doesn't affect the force that's being applied to the container. So the pressure will be the same for sample 2 because you still have the same number of particles that are exerting their force when colliding with the container. Now we're going to try example 14. So this question's a little different, although it looks really similar. It's still, N equals 8. It's still the same sample, but now they're asking you something different. So the container on the left only contains carbon dioxide. The one on the right has the carbon dioxide, but also some O2 molecules. Assuming that they behave ideally, which sample has the greatest density? So remember, density is mass over volume. And remember, the molar mass of carbon dioxide is 44 about, and the molar mass of oxygen is about 32 grams per mole. The volume of the container stays constant, but in sample 2, you're going to have a lower mass. Wait, sorry. I have to make sure I'm saying this right. Assuming that both samples behave ideally, which one has the greatest? Oh, yeah, I was going to say the wrong answer, but sample A is going to have the greatest density because it has more of the particles that have the higher molar mass. Sample 2 has some smaller molar mass. So if you could even add the total molar mass of all of them together divided by the volume. Volume doesn't change, but the mass in sample 2 is going to be less than the mass in sample 1. So therefore, you will have a greater density in sample 1 than 2. So the particle doesn't matter in terms of pressure, but it does matter in terms of density, because density is mass, which is, dependent on what molecule it is over volume. Last question is right here. So a gas is in a cylinder with a movable piston. The initial volume of the gas is 5 liters, and then it's compressed to 3 liters, and a new pressure P2. So there's a new pressure here. There was an original pressure here. Temperature is constant. What effect does this change have on the average kinetic energy of the particles? So if temperature is a measure of the average kinetic energy, which it is, then if temperature is constant, the average kinetic energy is going to stay the same. So because this has been stated, temperature is holding constant, let's say it's 50 degrees Celsius, then the kinetic energy, which temperature is a measure of, is going to remain the same. All right, that's all I have. I hope that helped.